Hello. So, in this video, we're going to be talking about vertical asymptotes and how we can sort of use limits to detect what they are or where they are. So, in general, we've done some work with limits on a whole bunch of different domain restrictions, right? Like when we were talking about initially how to use limits and we were talking about the right and left limits, we saw how that affected things like jump discontinuities. So in this one, we're going to be tackling vertical asymptotes, those kinds of domain restrictions, specifically to see how we can detect those with limits. So just as a quick reminder, vertical asymptotes, right? You've seen these in pre-calculus. It's these vertical lines where our curves sort of go off in sort of crazy directions. Sometimes they go in opposite directions, sometimes the same direction, but they sort of shoot up or down to infinitely large values. Okay. So if we want to figure out how to use limits here, we have to remember that they attempt to determine what the value of the function approaches as our x value approaches whatever the value of interest is, right? So in general, if we think about our vertical asymptote here, when we want to figure out the limit at this line, what the limit is going to try to tell us then is exactly what is happening to the function, sort of what it's doing as we're approaching that line. But this can be sort of already a bit complicated, as we can see in this example, right? Because depending on which way we're coming from, we have different behavior. For example, if we come from the right, we're going off to positive infinity. And if we go from the left, we're going to be going down to negative infinity. So this tells us sort of right off the bat that, as with most domain restrictions, it's going to be really important to think about this in terms of the left and right limits and not just sort of a limit overall. Okay, so the mechanics part of the limit is sort of going to be key here. So in particular, a vertical asymptote occurs when you have a ratio where the bottom is going to be shrinking down to 0 significantly faster than the top. And in particular, really what we want to look for, the sort of dead giveaway that is almost always the case, is that the overall ratio is going to approach this ratio of what is usually referred to as non-zero over 0, right? This nice mnemonic. So if we write this out in sort of math speak, right, we have this limit as we're going to some particular value, like x naught, of this ratio, right? Thing on the top, thing on the bottom. Thing on the top is going to some non-zero value, some c, whatever it is, 5, 1, pi, -8, whatever. But the bottom is going to 0, right? So we get this non-zero over 0 bit. So this is almost always the form that you're going to eventually see when you have a vertical asymptote. And those are sort of keywords there, right? Almost always. There are some exceptions we'll talk about. And eventually see, because sometimes this can be hidden, which we will also see soon. Okay. So again, to really sort of harp on the idea here, this is a process, not a point, right? So the limit as I'm going in, right, I want to think of it as the x value getting closer and closer and closer, and that means the output is getting bigger and bigger and bigger, right? Because you can't have infinity as a point, so you can't say I'm getting to the point x naught comma infinity or something. That doesn't make sense, right? So what we're really looking for is a situation where this thing is blowing up. It's usually what we say, right? It's getting really, really, really large. So it can be useful to sort of visualize what that means. So if we think about this f of x, right, this length here, this yellow length here, we think about that as the size of the top, right? Versus the g of x, size of the bottom, and then this ratio is sort of the overall value of taking that division, right? So we're doing sort of a geometric view of what's going to happen here. So on the one hand, as we're getting closer to a value, it's possible that that ratio is actually going to get smaller. So for example, as f of x gets smaller and g of x gets smaller, right, as you're getting toward the limit, that ratio might get smaller, not big. But eventually, the f of x has to stay sort of away from 0. It's going to go to some value, whereas g of x is going to get really, really, really small, right? F of x is going toward the c, which is not 0. G of x is going towards 0. So eventually, you're going to be dividing by something really small. And at that point, the ratio will sort of blow up and get really, really, really large, right? So the whole idea here is like, it might be unclear what's happening if you're not close enough, but once you get close enough to that value where g of x is getting really, really, really small, it has to get large because f of x is some bigger thing and you get a really large thing as a result, okay? So as mentioned though, there are other forms that can cause vertical asymptotes. So of the sort of non-obvious, right, if you don't have non-zero over zero, the sort of most common alternate form of that is going to be basically disguising the fact that you really have non-zero over zero. It's just not obvious yet. So for example, let's look at the limit as x goes to 0 of x over x squared. So you may look at that and immediately think like, oh, that's not simplified, right? Which is sort of the point here. But if I just sort of naively tried to use 0, right? If I just naively tried to plug it in and see what happens, well, I have x over x squared. I'm going to try to plug in 0. I get this 0 over 0. As a quick side note here, this is an actual sort of official math notation. I mean, you don't normally necessarily have a big blue arrow, but this arrow, this bigger arrow here, is saying that my left side is approaching the right side. And then the thing above it, which we can see right there, that x20, that's the condition causing that to happen. So this is saying that x over x squared approaches 0 over 0 as x approaches 0. So this is a less common but still widely used notation type. So if you see this in books or future classes with other professors and things, just be aware that that's what this is. Okay, so as a sort of, to be really clear here, because I have 0 over 0, I don't know what this is. It's not necessarily a vertical asymptote. Maybe it's a hole. It could be any number of things. 0, 0 is an indeterminate form. We don't know what this thing is. But what that's telling me is I need to figure out how to make it sort of not 0 over 0. And the key to doing that is to simplify. So I would take my x over x squared, simplify it down, right? That gets me 1 over x. Now, if I look at what happens as x goes to 0, this thing becomes 1 over 0. Now it's going to that non-zero over 0, right? So this is telling me that this thing was a vertical asymptote all along. Again, to be clear, I didn't know that when it was 0 over 0, right? That's sort of indeterminate. That doesn't, it's not clear what's happening. I only knew that once I simplified things and made it this 1 over x, which let me see that it was non-zero over 0, okay? So that's when I know, indeed, vertical asymptote at 0, despite the fact that it was sort of not obvious. It was hidden originally by that indeterminate form, okay? Okay, so the sort of very general math statement is that a vertical asymptote occurs when trying to take a limit from the left or right, you go to infinity. So that's the official statement, right? As mentioned, the vastly most common way of finding this is that you have this non-zero over 0. There are other ways of that happening, though. So for example, a much less common example, right, would be something like this, limit as x goes to 0 from the right of e to the 1 over x. So even here, we can sort of see that we still have a non-zero over 0 playing a part, right? So this is a common theme. But nonetheless, that's not the only thing happening here. And in fact, if we took 0 from the left, it'd be a good exercise to sort of work through on your own. You'll find that it actually doesn't go to infinity. So this is an example of where one side, it shows it's a vertical asymptote, whereas the other side, it doesn't. So it's an interesting example all on its own. Nonetheless, as mentioned, the most common type is still going to be some sort of non-zero over 0. So this should be sort of one of those Pavlovian, right, reflexes in your head. When you see this limit and you get non-zero over 0, your first thought should be, this is going to be a vertical asymptote. This is a domain restriction where I'm shooting off to infinity. And again, to be clear, just like in our very first example, it may be that one side goes to positive infinity and one side goes to negative infinity. So you have to do a little more work to figure out which infinity it's going to, but it's definitely getting infinitely large, just maybe in one direction or the other, okay? So in general, when it comes to vertical asymptotes, the idea is that we want to break down the domain restriction into these left and right parts, right? Because it may, even for the very same piece, go from positive or negative infinity. Fundamentally, what makes that restriction a vertical asymptote is that that limit is going to something infinitely large, positive or negative. Maybe both go positive, maybe both go negative, or they go to different places, but they're going to something infinitely large on at least one of those sides. And finally, sort of, I know I harp on this a lot, but it's because it really is true. The vast majority of the time that you're going to run into this is this non-zero over zero form, where maybe it's sort of not obvious that that's what it is initially, right? You might have to do a little bit of work with an indeterminate form, but either way, it's going to eventually end up being non-zero over zero almost always. Okay? So that is that.